Hello, everyone. Welcome to the second session for this week. Today, we are going to talk about Chapter 7. This is Amit Brambit, and the class is CS 110 for LaurelRidge Community College. Today, we are going to discuss Chapter 7 Problem Solving and Algorithms. Let me go ahead and share my screen. This chapter introduces the foundational ideas behind problem solving and the role that algorithms play in computing. Problem solving is at the heart of computer science because every program begins as a problem that needs a structure, logical solution. In this chapter, we explore various techniques for thinking through problems, breaking them down, and expressing solutions clearly. You'll see how computers problem solving follows a well-defined process and how algorithms, step by step, unambiguous instructions allow computers to carry out those solutions reliably. As we move through the material, you will connect traditional problem solving strategies to computational thinking and learn how these ideas translate into algorithm design, data structures, recursion, and searching and sorting techniques. This chapter builds the mindset needed to approach computing challenges systematically. Chapter goals. The first set of chapter goals lays out the major skills you will develop throughout this unit. We'll begin by describing the computer problem-solving process and relating it to George Polya's famous four-step method from how to solve it. You will also learn to distinguish between simple data types, those that hold a single value, and composite types, which group multiple values together. The chapter introduces two mechanisms for structuring composite data and helps you recognize when a problem is recursive. You'll learn to write recursive algorithms and understand differences between unsorted and sorted arrays. By mastering these goals, you'll strengthen your ability to model data, decompose problems, and select appropriate algorithmic strategies. The second set of goals focuses on algorithmic techniques for organizing and searching data. You'll learn how selection sort differs from insertion sort, and you'll examine quicksort algorithm, one of the fastest practical sorting methods. You'll also practice performing selection sort, bubble sort, insertion sort, and quicksort by hand to understand the mechanics behind each approach. Beyond sorting, you'll learn to apply the binary search algorithm, which operates efficiently on sorted arrays. Finally, you'll demonstrate your understanding by hand simulating these algorithms, an essential skill for tracing logic and understanding program behavior. These goals prepare you to handle data processing problems and evaluate algorithms' efficiency. Problem solving. Here, we see problem solving as the act of finding solution to a perplexing or unsettled question. In computing, the nature of problems can vary widely, but the central task remains the same: to identify what's being asked and determine a clear, effective path to the answer. The slide prompts you to reflect on your own definition of problem solving. Thinking intentionally about how you approach problems is essentially because programming requires a structured, analytical mindset. Before writing a single line of code, you must understand the problem deeply. This includes identifying key information, constraints, and the desired outcome. This reflective step sets the stage for more formal strategies introduced later. Polya's method. George Polya's famous problem-solving framework from how to solve it is given here. Although originally written for mathematics, Polia's method applies perfectly to computer science. Polia recognized that solving a problem involves identifiable stages, and his approach helps bring structure to complex challenges. In computing, Polia's ideas help guide algorithm design, understanding the problem, devising a plan, carrying out the plan, and evaluating the results. These steps encourage disciplined thinking and prevent jumping prematurely into coding. By adopting Polia's method, you'll learn to slow down, reason carefully, and develop more effective solutions. This slide highlights how timeless problem solving strategies directly connect to modern computational thinking. The four-step method. Here, the slide clearly outlines Polia's four well-known problem-solving steps. Understand the problem, devise a plan, carry out the plan, and look back. In understanding the problem, you identify what is known, what is unknown, and what is required. Devising a plan may involve selecting strategies such as breaking down the problem, drawing diagrams, or identifying patterns. Carrying out the plan is the execution phase where you perform the steps you designed. Finally, looking back encourages reflection. Did the solution work and can it be improved? This structured approach maps directly onto algorithm development, helping ensure clarity, correctness, and efficiency. Strategies. Ask questions. The slide emphasizes asking clarifying questions as an essential problem-solving strategy. Good problem solvers begin by interrogating the situation. What do I know? What information must be processed? What will the solution look like? Are there special cases to consider? And how will I recognize correct solution when I see it? These questions help eliminate ambiguity and ensure that your understanding is accurate before attempting a solution. In computer science, clear requirements often lead to incorrect algorithms or buggy programs. Asking questions refines your perspective, guides your planning, and prevents costly mistakes later in the problem-solving process. Here we focus on leveraging existing solutions. Don't reinvent the wheel. In both mathematics and programming, similar problems appear constantly in slightly different forms. Experienced programmers recognize familiar patterns and reuse known algorithms, techniques, or code structures rather than starting from scratch. This practice increases efficiency and reduces errors because proven methods are more reliable than untested ones. This slide encourages you to think of at least two similar problems you encountered, reinforcing that pattern recognition is a critical skill. Using existing strategies not only saves time, but also strengthens your understanding of general problem-solving principles. Divide and conquer. It's a powerful strategy that involves breaking a large problem into smaller, more manageable pieces. Each smaller problem can then be solved individually. This strategy ties closely to abstraction, allowing you to focus on one component at a time without becoming overwhelmed by complexity. The divide and conquer approach can be applied repeatedly until every subtask is straightforward to solve. Many famous algorithms, including merge sort and quicksort, use this technique to achieve efficiency and clarity. Understanding how to decompose problems is essential in programming and forms the foundation for modular design. Computer problem-solving process. Here, this slide maps the computer problem-solving process into distinct phases. First is the analysis and specification phase, where you analyze the problem and define what the solution must achieve. Next is the algorithm development phase, where you design and test the algorithm conceptually. Then comes the implementation phase, where you code and test the working program. Finally, in the maintenance phase, you use the program, update it, and correct issues as they arise. The recurring theme across these phases is iteration. Each step may require revisiting earlier phases as new insights or changes arise. This structured approach ensures that solutions are thoughtful, consistent, and adaptable. Phase interactions. This slide focuses on how the four phases of computer problem-solving process interact with each other. While the phases analysis, algorithm development, implementation, and maintenance are listed sequentially, real projects rarely progress in a straight line. The diagram shows arrows looping back because changes in one phase often require revisiting an earlier step. For example, if the problem definition changes, you may need to revise the algorithm. If code behaves unexpectedly, you may need to return to the analysis phase to ensure the requirements were fully understood. This slide asks, should we add another arrow? To reinforce that problem solving is iterative, effective programmers continuously refine their understanding, improve the algorithms, and update their implementation in response to new information. Algorithms, abstract versus concrete steps. Here we see definition of an algorithm, a set of unambiguous instructions designed to solve a problem in a finite amount of time using a finite amount of data. The slide distinguishes between abstract steps, which convey what needs to be done without specifying how, and concrete steps, where every action is fully detailed. Abstract steps help you think broadly about the algorithm structure, while concrete steps allow a computer to execute the algorithm precisely. Understanding this distinction is vital because algorithm development often begins with high-level abstract planning and gradually transitions into concrete executable instructions. The slide emphasizes clarity, precision, and finiteness as core characteristics of all valid algorithms. Developing an algorithm, two methodologies. There are two major methodologies for building computer solutions, top-down design and object-oriented design. Top-down design focuses on the tasks that must be completed. You start with the overall problem, break it into major components, and continue dividing until each part becomes simple and manageable. Object-oriented design, on the other hand, focuses on the data involved, organizing information into objects that combine data and actions. Although this chapter focuses more on top-down design, you will explore object-oriented design in detail later in Chapter 9. Understanding both approaches helps you to organize your thinking and choose the most effective way to express your solution. The summary of methodology. This slide outlines the typical methodology for developing an algorithm in a top-down fashion. First, you analyze the problem, ensuring you fully understand it and can articulate the requirements. Next, you list the main tasks, which will later become the main module of your program. Afterward, you write the remaining modules, breaking each main task into smaller subtasks until all steps are concrete. The final step is to resequence and revise as needed, ensuring the algorithm flows logically and completely. The process ends only when every module is concrete and fully specified. This slide reinforces the structured modular approach essential to solving complex problems efficiently. Control structures. It's a mechanism that determines the order in which instructions execute in a program. It asks you to recall the control structures defined earlier when discussing pseudocode functionality. These include sequence, selection, and repetition. Sequence refers to executing statements in order. Selection allows branching based on conditions, and repetition enables looping through statements multiple times. Understanding control structures is fundamental because they form the skeleton of all algorithms. Every program you write uses control structures to organize logic, respond to conditions, and process data iteratively. This slide reminds you that algorithmic thinking depends on combining these structures effectively. Algorithm with selection. This slide presents a selection-based algorithm for choosing the appropriate outfit based on temperature. It asks you to examine which statements are abstract and which are concrete. Abstract statements convey what should happen, such as choose appropriate clothing, while concrete statements specify exact actions like wear a heavy coat if the temperature is below freezing. This example demonstrates how decisions play a central role in algorithms. Selection allows programs to adapt to varying conditions and produce different outcomes based on input. By identifying the abstract and concrete steps, you gain insight into how to refine high-level logic into specific instructions that a computer can execute. Algorithm with selection. This slide continues with output selection example with a more formal representation titled Determine Dress. It demonstrates how abstract logic is translated into a structured decision tree. The flowchart style layout shows how the algorithm evaluates temperature ranges and determines what clothing is appropriate. This slide makes the algorithm's logic explicit by using clearly defined branches. It reinforces that selection is a powerful control structure that enables programs to choose among multiple alternatives. By studying how each branch leads to a specific outcome, you begin to understand how conditional logic shapes the flow of an algorithm and ensures that the output aligns with the input conditions. Looping statements. Count controlled loop. This slide introduces a count controlled loop, a loop that repeats a specific number of times. It asks why this type of loop is given its name. The answer is that the loop continues until a counter variable reaches a predetermined limit. Count-controlled loops are common in tasks such as processing each item in a list or running a procedure a fixed number of times. This slide demonstrates the structure visually and highlights how the loop depends on initialization, condition checking, and updating the counter. Count-controlled loops are predictable, easy to manage, and essential for many iterative algorithms. Event-controlled loop. Here we learn about event control loops. where execution continues until a specific event occurs. The slide asks you to consider what the event might be. Common examples include reading input until a sentinel value appears, repeating calculation until an acceptable approximation is reached, or looping until a user chooses to quit. Event control loops are powerful because they adapt to conditions determined at runtime, not by a fixed account. They require careful planning to ensure the event will eventually occur and the loop won't run indefinitely. This slide emphasizes how event control loops expand algorithmic flexibility. Calculate square root. This slide applies looping structure to real example, calculating a square root using iterative approximation. It asks whether any of the algorithm's steps are abstract, encouraging you to identify where high-level reasoning is used rather than explicit calculations. This illustration shows how guesses are refined through repetition. Since calculating a square root manually involves repeated improvement of guesses until they converge. This slide highlights how loops model mathematical processes. Understanding where abstract steps occur helps you refine them into concrete instructions for computation. The example bridges problem-solving techniques with iterative algorithm design. Calculate square root. So here we continue with the square root approximation example, demonstrating how iterative refinements works across multiple steps. The algorithm shows how an initial guess is repeatedly improved by applying a formula that gets the value closer to, let me get back to the slide. Okay, the value closer to the true square root. The slide again asks whether any steps are abstract, reinforcing your ability to distinguish between high-level logic, such as improve the guess, and concrete operations like performing specific arithmetic. The repeated appearance of this diagram emphasizes how essential iteration is in numerical methods. You can see how each guess becomes more accurate as the loop continues. This example illustrates that looping structures are vital not only in data processing but also in mathematical algorithms, requiring progressive approximation. Calculate new guess. Here we zoom in on the step where algorithm calculates a new guess during the square root approximation process. The question, are there any abstract steps, encourages you to evaluate whether the computation is a fully specified or whether parts of the process still need clarification. The slide highlights the iterative nature of refining a guess. Each iteration uses the previous estimate to compute a more accurate one. This provides a practical example of how loops and mathematical formulas work together in algorithmic design. It also encourages you to think carefully about when instructions need to be concrete for the computer and when an abstract step can still be useful during the planning. Here in this slide, we see the looping statements section, like showing the final structure of the square root algorithm as a whole. Although the visual diagram is featured without additional text, its purpose is clear. It demonstrates the overall flow of calculation, repetition, and refinement. You can see how initialization, repeated updating, and the stopping condition work together to form a complete loop. This reinforces the idea that effective loops require three components: starting point, a rule for repeating work, and a rule for stopping. By examining the full picture, you gain a comprehensive understanding of how the loops structure computational processes, especially in iterative numerical algorithms. I'll let you review this slide and let it sink in. All right, moving forward, composite data types. Here in this slide, we understand composite data types, structures that store multiple related pieces of data. A record is named heterogeneous collection in which each item is accessed by name. For example, a record called employee may contain fields such as name, age, and hourly wage. An array, on the other hand, is named homogeneous collection of elements, all of the same type, indexed by position. Arrays are useful for storing lists of numbers, names, or other repetitive data units. Understanding composite data types is crucial because they allow programs to group information logically and process it efficiently. They also serve as the foundation for more advanced data structures. Record example. Here we expand on records by showing how values are assigned to a record's individual fields. It represents a concrete example using employee record, setting the name to Frank Jones, the age to 32, and the hourly wage to 27.50. The accompanied figure illustrates how records store heterogeneous data under one unified structure. This helps demonstrate why records are useful. They organize related information in a clear, intuitive way. Similarly, programming languages often use structures or objects to implement this idea. The slide encourages you to see records as building blocks for representing real-world entities in algorithmic form. Array diagram. Here we see a visual diagram of an array containing 10 numbers. It shows numbered positions such as number 0 and numbers 4 to illustrate how array indexing works. Arrays allow efficient access because each element can be directly retrieved using its index. The diagram helps you visualize memory organization and understand how arrays form sequences of related values. This prepares you for later algorithms, such as searching and sorting, which operate heavily on array data structures. Arrays are one of the most fundamental data types in computer science because they combine simplicity with versatility. Storing data with a counter. Here we see that when reading data into an array, a counter is used to track how many elements have been stored. If the array is named list, then values occupy positions from list 0 up to list length -1. Having counter ensures you always know the exact range of valid data within an array. This especially is important in algorithms where you may not fill the entire array or where the number of elements varies with input. Understanding how to manage array boundaries prevents errors like accessing positions that haven't been assigned yet. This is a foundational skill for safe and effective array processing. An unsorted array. An unsorted array is simply a collection of data where the elements are not ordered. The figure shows an array with values arranged arbitrarily. Unsorted arrays are common in real-world input because raw data rarely arrives in sorted form. Many algorithms, such as sequential search, assume no particular order. Later, the chapter will show how sorting transforms arrays to make searches faster and more efficient. This slide prepares you for understanding the trade-offs between using raw unsorted data and taking the extra step to sort it. Composite data types, filling an array. Here, we see an example of filling an array named numbers with values based on limit variable. The figure illustrates how the array is populated element by element. This demonstrates how loops and arrays work together. A loop controls how many values are inserted, and the array provides the storage structure. Understanding how to fill arrays is essential because many algorithms, sorting, searching, statistical calculations, operate on arrays of values. The slide reinforces the connection between data structures and looping patterns learned earlier. Sequential search of an unsorted array. The slide defines sequential search algorithm, one of the simplest ways to locate an item in an unsorted array. In sequential search, each item is examined in turn and compared to the target value. If a match is found, the search stops. If not, the algorithm continues until all items have been checked. The slide emphasizes that the loop ends under one of the two conditions. Either the item is found or the entire array has been examined without a match. While sequential search is not the fastest method, it's easy to implement and works for both sorted and unsorted arrays. This foundational algorithm sets the stage for comparing more efficient searching techniques later. Sequential search algorithm diagram. Here's the diagram of sequential search algorithm. It visually breaks down each step involved when scanning through an array to find target value. The flow begins by initializing an index and checking whether the current item matches the target. If it does, the algorithm reports success. If not, the index increments and moves to the next element. The loop continues until either the value is found or the array is exhausted. Here we see that the linear nature of sequential search. There are no assumptions made about ordering of the data. And by following this illustration, you can clearly see how the algorithm progresses step by step, reinforcing how conditions and iterations work together to control the flow. Booleans. Boolean variables and Boolean operators such as and, or, and not, are important part of understanding. A Boolean variable can hold only one of the two values, true or false, making it essential for controlling decisions in programs. AND operator requires both operands to be true to return true, while OR returns true if at least one operand is true. I hope this reminds you of last week's sessions where we went over several of the gates in integrated circuits. Not flips a value, returning true when the operand is false and false when it's true. These operators form backbone of conditional logic, enabling algorithms to make decisions, check conditions, and evaluate expressions. Understanding Boolean logic is crucial because it appears everywhere in the programming, from loops, tests, to filtering data, to implementing complex conditions. Sorted arrays. Here we understand what makes an array sorted. So simply, values are arranged in either ascending or descending order based on a key, a field, or value used to determine ordering. A sorted array allows more efficient operations, especially searching, since relationships between elements are predictable. Sorting algorithms rearrange the elements so the array satisfies this ordering requirement. The slide emphasizes that sorted arrays rely on keys with clearly defined relational operators, so comparisons can be made consistently. Understanding sorted arrays is foundational for learning more advanced algorithms like binary search and various sorting techniques. Sequential search in a sorted array. Here we understand how sequential search behaves differently when the array is sorted. Unlike an unsorted array search, where every element must be checked, a sorted array allows the algorithm to stop early. Once the search encounters an element greater than the target, it knows the target cannot possibly appear later in the array. This improvement reduces unnecessary comparisons and increases efficiency. The slide poses the question, is this better? To prompt you to reflect on the advantage of early stopping, while still not as efficient as binary search. Sequential search on sorted arrays is undeniably improved thanks to the inherent structure of the data. Here we see a visual example of sorted array of integers. The diagram provides a concrete illustration of concept introduced earlier, values arranged from smallest to largest. Seeing the numbers placed in correct order helps highlight the predictable relationships sorted arrays create. This ordering is essential because it forms the basis for efficient searching algorithms like binary search. The visual representation also helps you understand why sorted arrays are so valuable. It's easy to reason about where a number might be found simply by comparing it to the values already seen. A sorted array. Here we see visual exploration of sorted arrays. Although it contains mostly imagery, the purpose is to reinforce how searching through a sorted list provides natural structure. As we see, you read in the array of values, then you write enter value for which to search, then you read search item, then set found to be true if search item is there. If we find the item, we say item is found, else we write item is not found. You can easily predict how a search progresses because elements increase in order. This prepares you for the logic of binary search, where the array is repeatedly divided based on the relationship between target and middle element. So let the algorithm sink in. Okay, let me get back to the slide again. Okay, the third slide for sorted array. Here we see how a simple algorithm can help you find an item in an array. So set found to true if search item is there. So first you set the index to be 0, then you set found to false, and then you loop saying you loop until index is less than length and not found. And basically the conditions, if you look at the if else block, if else area of the code of the algorithm, it says it sets the found to true when it's uh, when data at that index equals to the search item. And basically it will break out of the loop if any of the if else if conditions are met. So let this algorithm sink in. For sorted array. Moving on to binary search. Okay. Basically, we contrast it with sequential search. Sequential search always starts at the beginning of and checks each element in order. And binary search requires a sorted array. Instead of scanning linearly, binary search looks at the middle element first. If the target equals to the middle value, the search ends. The target is smaller, the search continues only in the left half. If it's larger, it's only in the right half. Each comparison cuts the remaining search space in half, making binary search dramatically faster than sequential search for large datasets. This slide lays groundwork for understanding one of the most famous and efficient searching algorithms. Here we see a visual representation for binary search in action. Here we see how the search interval narrows with each comparison. Basically, Boolean binary search makes you set some of the variables first and then loop until the condition of first is less than last and not found satisfy, and basically divide the data into half each time you go through that while loop, reducing the search space further, and then return when the item is found. So let this algorithm sink in. You see how it visually divides the array into half, and then binary search can quickly eliminate large portions of the data. And I hope it clarifies the logic that after examining middle value, only the relevant half remains worth exploring. This repeated halving process continues until the target item is found. The search interval becomes empty. Uh, and either of those conditions would stop the search. And this slide is very important for any of you who are trying to get into big tech or developer role in general. It's very important to learn binary search. So let's move on to the next slide, which is also about binary search. Here, the slide represents a concrete example of binary search along with a trace of showing each step. By following the trace, you see exactly how the search narrows and which comparisons occur at each stage. The example connects the abstract idea of halving the search space to the specific numbers being tested. This helps reinforce how binary search behaves predictably. Check the midpoint, decide left or right, and repeat. The trace provides insights into algorithms' efficiency by showing how few steps are required to locate value. This slide strengthens your understanding by combining theory, visuals, and worked example. Oh well. Um, while I'm just going through these slides pretty quickly, I hope you can look up binary search example videos on YouTube or just search it, and you'll find a lot of good examples, a lot of good articles written on this specific concept. Here we are in this slide, we are searching for, first of all, we are searching for cat, and then we are searching for fish, and then for zebra. And then we see each iteration that how the search space becomes smaller. And then first, when we are searching for cat, we get true by the fourth iteration. Searching for fish, we get true by the third iteration, and so on. But if I don't know if this example makes really good sense or not, let this sink in. Maybe you can pause the video and look through this and try to understand it deeply. And if not, please do look up more examples because it's not a concept that can just be taught within 3 or 4 minutes of slides. Moving on. Here, this slide asks question if binary search is always better. With the included chart that shows average number of comparisons required by sequential versus binary searches. While binary search is dramatically faster for large data sets because it reduces the search space by half with each step. Its advantages only apply when the data is already sorted. If the list is unsorted, preparing it for binary search requires sorting first, which may outweigh the performance benefit for small data sets or one-time searches. Sequential search, although slower, works on any datasets and requires no preprocessing. This slide helps you understand that algorithm choice depends on context, data size, ordering, and how often the search will be repeated. It reinforces the idea that algorithm efficiency is not absolute. It must be judged within a real problem scenario. Moving on to sorting and why sorting matters. Sorting is the process of arranging items based on one or more sort keys. Sorting is crucial because it makes data easier to search, analyze, and manipulate. Many algorithms rely on sorted data to reach optimal performance, including binary search and numerous optimization routines. The slide asks an important question. Why is sorting important? Sorting improves efficiency, reveals structure in data, and can even reduce complexity in downstream tasks. For example, sorted datasets simplify tasks like detecting duplicates, generating reports, comparing values, and locating items quickly. This slide sets the stage for the sorting algorithms you are about to study, helping you appreciate why sorting is one of the most fundamental operations in computer science. Selection sort, the basic idea. Here we see the core logic behind selection sort using a list of names as the example. The algorithms repeatedly find the smallest remaining item and moves it into its correct position. The manual analogy helps visualize the process. You write the smallest name on a new sheet, cross it off the old list, and repeat. By the end, you have the same list but fully sorted. Although simple and intuitive, selection sort is not the most efficient algorithm for large datasets because it repeatedly searches the unsorted portion of the list. However, it clearly makes it ideal for learning the basics of sorting. The slide introduces the fundamental loop structure and idea of choosing the next smallest element. Selection sort the in-place version. Here is a more efficient way to apply selection sort without using a second list. Instead of writing values somewhere else, each time you find the smallest item, you swap it directly with the item in its correct position in the original list. This eliminates the need for extra storage space and reduces overhead. The slide highlights that crossing off an item naturally creates a free space, which can be filled by swapping values rather than rewriting them. In this in place approach is how selection sort is typically implemented in code. It demonstrates how conceptual algorithms evolve into practical, memory efficient forms used in programming. Here we see a visual example, a figure showing several steps of selection sort process with sorted elements shaded. The visual emphasizes how the sorted portion grows from left to right as each smallest element is identified. You can see algorithm isolate the next minimum value, swap it into place, and gradually convert the array into sorted order. This diagram helps reinforce the pattern. Find the minimum, place it at the front, and move the boundary of the sorted portion. Seeing each step visually helps you understand how selection sort systematically reduces the unsorted region and maintains a clear sense of algorithmic process. Again, I would reiterate that, if this example is not very clear, you can pause the video and look at the slide and let it sink in. Let's move on. Here we continue with a visual walkthrough of the selection sort. This is largely graphical. It reinforces systematic nature of the algorithm. Here we use this algorithm to determine dress based on temperature. If you remember, we went over similar example in our previous lecture of selecting dress based on the temperature. Each iteration selects the smallest remaining value and places into the next available position. Examining multiple stages, you can better appreciate how predictable and mechanical the process is. Moving on to the next slide with another example of finding smallest unsorted item. We see that first we are setting index of smallest to the first unsorted, then we set index to the first unsorted plus 1, and then we loop in a while loop until index is less than or equal to length minus 1. What the while loop does is checks a condition if data at that index is less than data at the index of the smallest. And if that condition is true, it will set the index of the smallest to the index. And coming out of the if condition, we set index to index plus 1. It always performs the same number of comparisons regardless of whether array is nearly sorted or completely random. This helps you understand both the simplicity and its limitations. The slide prepares you for upcoming comparisons with more efficient sorting methods. So let this sink in. Again, you can pause the video and let the algorithm sink in and better understand it the best way you can. Also, I would suggest that you look up this topic via different uh, articles and videos so that you can better understand it. There are a lot of good graphical examples out there that will explain this topic even better. So final slide on selection sort is about swapping the first unsorted with the smallest. And here we see the 3 lines of this algorithm, the pseudocode that says set the temp item to data at first unsorted, then set data at first unsorted to data at index of smallest, and then set data at index of smallest to the temp item. So here we see use of the temporary variable to do the swap operation of the selection sort. So by putting the first unsorted item into temp item, we are allowing that place to be filled with data at index of smallest in the second line, and then we are placing the temp item into the data of the index of the smallest. Let's move on to the next slide called bubble sort. Here is another example of sorting algorithm. Like selection sort, the goal is to find the next item to place, but bubble sort uses a different strategy. It works from the end of the list upward, comparing adjacent pairs of elements and swapping them when they are out of order. Each pass bubbles the next smallest element towards the front of the array. The slide lays out this process clearly and highlights that bubble sort repeatedly scans the list, making swaps until the entire array is sorted. While the bubble sort is conceptually easy, it generally is slow because it requires many comparisons and swaps. Here is a visual example of how bubble sort works. Each step illustrates how adjacent pairs are compared and swapped when necessary, causing smaller elements to move upwards through the array. The visuals make it easy to follow the ripple effect that gives bubble sort its name. By examining the process visually, you see why bubble sort often requires multiple passes. It only moves elements one step at a time. This slide prepares you to understand why bubble sort performs poorly on large data sets but remains valuable for educational purposes due to its simplicity and clear behavior. Bubble sort is very slow. Why is that the case? Well, it works by repeatedly comparing and swapping adjacent pairs, and each pass only moves an item one position at a time. The algorithm often requires many passes before the list becomes fully sorted. The slide asks two critical questions. Can you see a way to make it faster? And under what circumstances bubble sort fast? Well, bubble sort can be improved by detecting whether any swaps occurred in a pass. If none did, the list is already sorted. It also performs relatively well when the list is newly sorted, since fewer swaps are needed. This slide pushes you to think about algorithmic efficiency and how data characteristics impact performance. So we continue with bubble sort demonstration with another visual sequence of comparison and swaps. These steps will help you understand how the bubble sort gradually bubbles up. Smaller values to the beginning of the list and pushes larger values towards the end. Although it's just an algorithm, I hope you can pause it and let it sink in, as it reinforces the repetitive mechanical nature of bubble sort. You can clearly see how each iteration would modify the array, one local swap at a time. And the purpose here is to prepare you to trace bubble sort manually and analyze its performance characteristics, especially how many swaps are needed to sort different patterns of data. And here is the final visualization for bubbling up. Here we see the list reaching its sorted state. After many successive comparisons and swaps, we see basically we are in the algorithm, we are setting the index to length minus 1. So say your length is 7 elements and index is 6. And then you run in a while loop when index is greater than first unsorted. And then you basically have an if condition where data at index is less than data at index minus 1. And then you keep on swapping the data at index and data at index less than 1, data index minus 1. And then you set swap to true when that happens. And coming out of the if condition, you set index to the value index minus 1. And that algorithm basically helps you bubble up the value. Let's move on to the next sort topic called insertion sort. So beginning with the simplest idea, if you have only one item, the list is already sorted. With 2 items, you compare them and swap them if necessary. With 3 items, you place the third item in the proper position relative to the first 2, effectively inserting it into the correct location. This pattern continues as the list grows. Insertion sort builds the sorted list one item at a time, inserting each new item where it belongs. This process mirrors how people sort playing cards in their hands, one card at a time, always maintaining order. The slide establishes insertion sort as a simple, intuitive, and efficient algorithm for small or nearly sorted data sets. Insertion sort bubbling up. So here we see how the newly inserted item can be bubbled up into place. This means that as you insert the new element, it shifts backward through the sorted portion until it reaches its correct position, similar to the bubbling motion seen in bubble sort. The visual figure provided helps you follow each element moves relative to the sorted segment. This reinforces the fact that insertion sort combines elements of ordered growth with localized adjustments. The algorithm is efficient for data that is already mostly sorted because fewer shifts are required. This slide visually demonstrates how insertion works in practice. Here we see an algorithm of insertion sort. We see a visual depiction of the algorithm. The diagram shows how the sorted portion expands as each new item is inserted. You can trace the movement of values as they shift to make room for new element. This visual reinforces the mechanics of insertion sort, helps you understand how it maintains sorted region at the beginning of the array. By sorting the complete process, the slide builds your confidence into tracing insertion sort manually and recognizing how it differs from selection and bubble sorts. So I'll let it sink in. And I suggest that you pause the video and try to understand this algorithm in detail for yourself here. Let's move on to subprogram statements. Introducing subprograms. Here we try to understand the concept of a subprogram, which is a named block of code that performs a specific task. When the subprogram's name appears in another part of the program, execution temporarily jumps to the subprogram. Once the subprogram completes its task, execution returns to the original location. Subprograms help organize complex programs into smaller, manageable units, improving readability, reuse, and maintainability. This slide emphasizes the importance of modular design and introduces you to the idea that the program can call other pieces of code to perform specialized work. This structure is foundational for all high-level programming languages. Parameters and arguments. Here we describe how data is passed into subprograms. Parameters are the identifiers listed in subprograms declaration. They act as placeholders for incoming values. These are often called formal parameters. Arguments are the actual values or variables provided when the subprogram is called, known as actual parameters. This distinction is crucial because it shows how information flows between different parts of a program. It also introduces the concept of input to subprograms, allowing them to behave flexibly based on the provided data. Understanding parameters and arguments is key to writing clean, reusable modular code. Flow of control. Here is a diagram illustrating the flow of control when a subprogram is called. The program pauses the main execution, transfers control to the subprogram, executes its instructions, and then returns to calling point. The diagram helps you visualize how the program's execution path changes temporarily. Understanding this flow is essential, especially when dealing with nested subprogram calls or more complex program structures. This slide reinforces the importance of organizing program behavior into separate, reusable units and understanding how control passes between them. Return flow. This slide continues to show the visual explanation of subprogram control flow. It highlights how the program resumes execution exactly where it left off and after the subprogram finishes. This ensures logical continuity and predictability. The slice diagram underscores that subprogram calls create a temporary diversion in program flow, but ultimately return to the main logic. The behavior lays groundwork for more advanced ideas such as recursion and stack frames. By understanding how control moves in and out of subprograms, you can better structure your algorithms and maintain clarity in large programs. Recursion. It's a powerful idea that a subprogram can call itself. Recursion is especially useful for problems that can be naturally divided into smaller versions of same problem. The slide identifies two essential parts of recursive algorithm, the base case, which is the simplest instance of the problem that has a direct answer, and the general case, which expresses the solution in terms of itself but with a smaller input. Without proper base case, recursion would continue forever. This slide lays the conceptual foundation for understanding recursive thinking, showing that recursion is not mysterious. It's simply structured way to repeatedly break down a problem until it becomes simple enough to solve directly. Here's a factorial example to illustrate recursion. Factorial is defined as n factorial equals to n multiply n minus 1 multiply n minus 2, etc., all the way to 1. The slide shows how the definition naturally splits into a base case and general case. The base case is factorial 0 equals 1. The general case is factorial n equals n multiplied by factorial n minus 1. This makes factorial classic example of recursion because the definition itself is recursive. The slide helps you see how the recursion captures repetitive patterns elegantly and compactly. Understanding this example is crucial as factorials form a stepping stone for mastering more complex recursive algorithms in computing. Here's a visual breakdown of how recursion unfolds step by step. Each recursive call breaks the problem into a smaller unit until one base case is reached. The diagram likely illustrates stacking calls factorial 4, calling factorial 3, which calls factorial 2, and so on. You see the first block has 4 lines where you write enter n, then read the number, set the results to factorial n, and then write results of e is the factorial of n. The second block shows how factorial n comes about with the if and else statement, where if n is 0, return 1, else you return n multiplied by factorial n minus 1. Here is an example of recursion with binary search that we discussed a few slides back. I'll suggest that you pause the video and let the algorithm sink in. It has an if and else block. First of all, we check if the first is greater than last. If so, we return false. Else, we get into the second block where we set middle to the middle number of first addition of first and last divided by 2. And if the item equals to the middle number, then we found the number we are looking for. In binary search, we return true. Else, we keep on dividing the array into half of the original size and continue through the if and else block given next to it. So let's move on to the quicksort. It's one of the fastest and most widely used sorting algorithms. The principle highlighted here is simple. It's easier to sort smaller lists than larger ones. The slide shows how dividing datasets A, F, G, L, M, R, S, Z, etc. makes sorting more manageable. Quicksort embraces the idea by splitting a list into smaller segments, sorting those segments and combining the results. The diagram helps you see how breaking data into logical range sets the foundation for a divide and conquer approach. The slide motivates why quicksort outperforms the algorithms like bubbles or selection sort. So we're going to pause our video here and I'll be recording another set of videos continuing from this quicksort. So see you in the next class. Bye.